Hello and welcome to this explainer. Listen, I am absolutely pumped you're here right now. Today I'm putting on my masterclass tutor hat, and we are going to completely hack your GCSE Physics Paper 1. If you've been staring at your textbook, feeling like energy stores and circuit diagrams are basically written in an alien language, please don't worry. I am right here to translate the whole shebang for you. We're going to cut through all the noise, completely ditch the fluff, and focus specifically on those high-yield concepts you absolutely need to smash those higher-tier exams. Here is our game plan for the lesson. First up, energy stores and transfers. Number 2, electricity, moles and coulombs. Third, those notorious series versus parallel circuits. Fourth, demystifying circuit diagrams. And finally, we'll cover the exact steps you need to absolutely ace the required practicals. All right, let's get straight to it.
Section 1. Energy stores and transfers, the roller coaster. Okay, let's dive right into this. To start off, we basically need to completely change how you think about energy. It's not magic. It's honestly just a simple accounting game. The rule is that energy is always conserved. You cannot create it, and you literally cannot destroy it. You can only transfer it between different stores. Let's look at a classic exam scenario. Where exactly does the energy go when a roller coaster drops? I want you to picture a car being held totally stationary at the very top of a massive drop. Right at that exact moment, it has zero kinetic energy, because, well, it's not moving. But it is fully loaded with gravitational potential energy, or GPE. Now, the second those brakes release and it plummets down the track, that GPE store rapidly decreases, transferring directly into its kinetic energy store.
Now, here's the absolute best math hack this unlocks. Because energy is always conserved, the GPE lost at the top exactly equals the kinetic energy gained at the bottom. The equation for GPE is mass times gravitational field strength times height. The equation for kinetic energy is a half times mass times velocity squared. If you set those two equations equal to each other, you're going to notice something awesome. Mass is on both sides. That means mass completely cancels out. By rearranging this, we find that velocity simply equals the square root of 2 times gravity times height. You literally only need the height it falls from to calculate its exact speed at the bottom. It doesn't matter if it's a heavy roller coaster or a tiny marble, the math is totally elegant and a massive time saver when you're in the exam.
Moving on to Section 2. Electricity, moles and coulombs.
If energy is the currency in our little accounting game, electricity is the delivery system. It's really just the flow of charge, specifically electrons, carrying energy from a source, like a battery, all the way around a circuit to a component, where that energy is finally released. But to truly get electricity, we need to understand how we count these charges in the first place, and that brings us to coulombs. Look, electrons are incomprehensibly small. There are so incredibly many of them flowing through a wire that counting them individually would be, well, impossible. So we group them. Think of it exactly like how we use moles in chemistry to group atoms together. A coulomb is just a specific massive grouping of electrons. We really don't care exactly how many individual electrons are in the group, we just package them into these convenient coulombs to actually make the math manageable.
And knowing that makes understanding voltage or potential difference so much easier. When you buy a battery rated at 1 volt, what does that actually mean? 1 volt simply means exactly 1 joule of energy is being given to every single coulomb of charge that passes through it. So a 6-volt battery. It supplies 6 joules of energy to every coulomb. Those little coulombs then travel through the circuit, and when they pass through something like a light bulb, they have to drop off all 6 volts worth of that energy as light and heat before heading all the way back to the battery to re-energize.
Section 3. Series versus parallel circuits. Now that we've got the delivery system down, let's talk about the actual roads they travel on. Examiners absolutely love to set traps here, but we're going to walk through these rules together because they are basically exact opposites. In a series circuit, which is just one single loop, the total potential difference from the battery is shared between the components, but the current is exactly the same everywhere. And the total resistance is just all the resistors added together. Simple enough, right? But then in a parallel circuit, where the road actually splits into branches, the potential difference is the same across every single branch, while the total current is shared between those branches. Oh, and here's a fun twist. Adding more resistors in parallel actually lowers the total resistance because you're giving the current more routes to flow through.
So the crucial point is this exam hack right here. In a series or a potential divider circuit, how do you quickly figure out which component gets most of the energy? The ultimate rule of thumb is that the component with the greater resistance simply gets the greater share of the total potential difference. For example, if you have a 20-ohm resistor and a 10-ohm resistor sitting in series, that 20-ohm resistor is going to hog twice as much voltage as the 10-ohm one. Lock that into your memory, and I promise you will completely fly through those potential divider calculations. Let's tackle Section 4, Demystifying Circuit Diagrams.
This is an area where examiners are literally waiting to trip you up. But honestly, once you understand the physical reality of what's happening inside the wires, these current voltage or IV graphs become incredibly logical. An ohmic resistor gives you a perfectly straight line right through the origin. Voltage and current are directly proportional, easy. But for the filament lamp, it curves. Why? Well, because as you increase the voltage and current, the metal wire gets really hot. The metal ions in the lattice start vibrating more and more violently. The flowing electrons start constantly colliding with these vibrating ions, making it much harder for them to pass. Therefore, the resistance increases as the current increases, creating that signature curve. And finally, a diode has a flat line that just suddenly shoots up. Because it acts like a turnstile, it only allows current to flow in one single direction.
Okay, pause. Listen really closely to this exam warning. First off, never ever draw a tangent on a curved filament bulb IV graph. It tells you absolutely nothing useful. Just pick a point on the line and use Ohm's law, V equals IR. That's it. Second, and this is actually wild, over the past few years, certain exam boards have completely messed up their own mark schemes by suggesting a standard resistor's resistance increases with temperature. That is flat out wrong. Standard resistors are engineered from special materials specifically so their resistance stays perfectly constant, even if they get super hot. Stick to the actual science. A standard resistor always has constant resistance. And this brilliantly illustrates exactly why we have special components like thermistors and light-dependent resistors, or LDRs. These guys do the exact opposite of standard metals. For a thermistor, as the temperature rises, its resistance actually drops. And for an LDR, as the light intensity rises, its resistance drops. This makes them absolute magic for building automated sensors. If you put a thermistor into a potential divider circuit, boom, you've got a thermostat for your central heating. Throw an LDR in there, and you've got a smart sensor that automatically turns on a street lamp the second the sun goes down.
Finally, Section 5, Acing the Required Practicals.
For this final part, we're going to focus entirely on the exact, foolproof steps you need to bag full marks on your practical questions. First up is the thermal insulation practical. It's incredibly straightforward if you just list your steps cleanly. Step 1. Take identical metal cans and wrap them in different insulating materials, or just use different thicknesses of the exact same material. Step 2. Pour the exact same volume of hot water from a kettle into each can and secure a lid that has a thermometer in it. Step 3. Start a stopwatch and measure the temperature decrease over a set period of time, let's say 10 minutes. The can with the smallest temperature drop clearly has the best insulation. Boom! Full marks. Let's move on.
Next is the resistance of a wire practical. Step 1. Tape a long metal wire to a meter ruler and attach crocodile clips to it, linking it into your circuit. Step 2. Read the voltmeter and ammeter and use Ohm's law. Remember, resistance equals voltage divided by current to calculate the resistance of that specific length of wire. Step 3. Move one crocodile clip further down the ruler to increase the length and simply take the readings again. Step 4. Plot your calculated resistance against the length of the wire on a graph. If you've done everything right, you'll get a beautifully straight line going straight through the origin, brilliantly proving that resistance is directly proportional to the length of the wire.
Wow, okay, we have covered a massive amount of ground today. We went from the elegant math of energy conservation to the tricky physics of vibrating metal ions in your circuits, right through to the exact step-by-step methods for your practicals. You now have the exact blueprints to completely dissect these questions. But let's be real, passive learning only gets you so far. As our source material suggests, to truly lock this in for your final mocks, you absolutely need to test your speed and recall, perhaps by jumping into some rapid-fire practice on the Science Charts app. So I'll leave you with this provocative thought. You know the rules, you've got all the hacks, but when that timer actually starts in the cold, quiet exam hall, are you fully ready to execute? Keep practicing, stay focused, and go absolutely crush that paper.